Lately, we've been playing with equations of this form, differential equations of this form. P of xy times dx plus q of xy dy equals to 0. And in our last topic, we studied the kind that were called exact differential equations, where these two come from partial derivatives of another function. Well, what if this is not an exact differential equation? What can you do with it? And an idea crops up in lesson 10 about the integrating factor. An integrating factor is something that you can multiply this equation by in order to turn it into an exact differential equation. Now, the book says something, I think, rather tantalizing. It says that theoretically this exists for every inexact differential equation. But also points out that there's no certain way to finding out what this integrating factor is. Now, the author does cover a couple of very specialized examples in lesson 10. And so he shows that we're able to solve a few of these under the right circumstances. But in general, we don't know what this is that would turn this equation from an inexact differential equation to an exact differential equation. And more than likely, I would suspect that, in fact, I would expect that integrating factor in many cases, most cases perhaps, is a function that we wouldn't recognize. It's not in a form that we would recognize. It would have to be expressed as, say, an infinite series. So it gets complicated there. Well, I've decided that lesson 10 is really not all that useful because it only works for very specialized examples. However, we're going to go on to lesson 11, which deals with another type of integrating factor. And these types of problems are actually pretty useful. They do show up in some applications, and so it's a common enough type of equation and simple enough that we should study it. All right, so it's known as the first order linear differential equation, and it looks like this. Y prime plus p of x y equal to q of x. Alright, so this is, let me get the exact wording there our book uses. Calls this the linear differential equation of first order. Okay, well, it's a first order equation because we have a first derivative only. We don't have second or third derivatives, for example. And it's linear because this dependent variable y is a linear term. It's not y squared or y cubed, it's just y to the first power. All right, well, notice also that these functions are only functions of x. Now, we could turn this into a differential form type of equation because y prime is dy over dx. If I multiply it through by dx, then it turns into a differential form equation. You could turn it into something that looks sort of like an exact differential equation, but wouldn't necessarily be one. Anyway, it turns out it's easier to think of it in this form, in the derivative form of a differential equation. All right, so we're after an integrating factor, and I'm going to say I, which is a function of x, is an integrating factor. Now, we don't know what that is yet, and I want to develop it to show you what it is that works. And I think this is, to me, fascinating. Because when I first saw this many years ago, decades ago, as an undergraduate, I just thought this technique that we're about to learn was kind of magical. In fact, I asked the professor, how did they come up with this? How did they figure this out? And he clearly hadn't thought about it. He just said, years of research. Okay. Well, I don't know about years of research. But let me just go ahead and develop it for you, because I think it's interesting to find out here. All right, so here's the idea. I have a function, as yet unknown, I, that when I multiply this equation will now make that equation solvable. All right. So now let's look at it just to save some writing and make it look a little simpler. Let me think of it as y prime plus py equals to q. Bear in mind, though, that p and q are functions of x, as is I. I is a function of x. So I'm going to multiply my equation by my integrating factor. This gives me I y prime plus I py equals to iq. So you have to ask yourself, well, what was gained there? Well, here I think is the big leap. This is a big leap. And incidentally, this technique, multiplying by integrating factor, if you take a lot of math, if you're a math major, you've gone through lots of proofs, you start to learn all kinds of nifty little tricks to try in solving problems, improving things, or developing ideas. And this is just one of many things in our toolbox. Multiply an equation by an unknown function, and if you get it to work the way you want, maybe you can figure out what that function has to be. Hope that made sense. Okay, so, but here I think is now we have to make a big leap. We have to say, well, this kind of resembles a product rule derivative. Wouldn't it be nice if the left side was the derivative of the integrating factor times y? If it was, then perhaps we can solve this thing. Because when I bring the dx over here, I've got iq dx. That's solvable because I can integrate this differential, get I times y, and theoretically I can integrate the right side because each of these functions is a function of x. There are no y's on this side. So really it turned into a separable differential equation. And then we can finish by dividing by our integrating factor. So our solution would be y equal to the integral of the integrating factor times q dx divided by the integrating factor. Alright, well, that still doesn't get us there yet. We still don't know what that function has to be. But this is I think a pretty major leap, and someone had to think of this. Okay, I think this is pretty remarkable. But this is where the so-called years of research comes into play. I guess someone thought of this idea and said, well, let's run with it and see what happens. All right, so, and let's do exactly that. Let's see what happens. So let me do a little erasing here. I want to expand this derivative out. So, derivative with respect to x of this product. All right, well, we have a product rule, so it's going to be I prime times y plus I times y prime equals to iq. Alright, now I want to set this part equal to that part. And, okay, so we'll do that. And notice that if this was equal to this, then these two terms cancel off. They would subtract off. So in other words, I have IPY would have to equal to I prime y. So that's IPY would have to equal to I prime y. So that would be the prerequisite, so to speak, of finding my integrating factor. In this format, if this is going to work, then these two have to equal. Now look at that over here. IPY equals I prime y. We can divide y off from both sides. It's a small miracle. Okay? And if I divide by I have P equals to I prime over I. Okay, so if we go to some kind of differential form, P would equal to I prime is differential of I with respect to x, all divided by the differential of I. So if I multiply this little equation by dx, I have p dx equals to di over I. So let me make some room here, do some erasing. But here we've reached a good end because we can solve that little differential equation, can't we? All right. So let me make some room here. I erased all this junk and I rewrote this up here. So let's go ahead and dispense with this part of the board. Okay, I have differentials on both sides. My variables are separated. That means I can integrate. Now, I don't know what this without specifically knowing what p is yet. You know, we don't have a real problem in front of us. I don't know exactly what that's going to be, so we'll just have to keep that as p dx. But the right side is a logarithm, isn't it? It's the natural log of our integrating factor. And for various reasons, let's leave the constant out. I haven't really looked into that, but I have a feeling it just adds nothing to the problem to do the additive constant. So we can actually, it turns out we can safely ignore it. All right, well, so what's the integrating factor? To eliminate the log, I have to make both sides a power of e. So that means that the integrating factor, I, which is a factor, which is a function of x, is equal to e to the integral p dx. E integral p dx. All right, so this is the secret to this type of problem. The integrating factor is e raised to an integral of this function, dx. So let's leave it at that, and we'll go on and work a few problems to exploit this idea.